Okay, so the first slide is more like a hypothetical view of how things are done in a digital environment. So we actually have separate memory block. Historically, again, we are heading towards a generation where memory and processor will kind of be merged at some point. We are trying to go towards logic in memory or process in memory, but without heading to that, cutting edge realm. Let's just stick to the basics for the time being. Whatever we can use in our day-to-day devices. We have a separate memory block, and we have a separate processing unit, which is often mentioned as data path. We'll talk about that. But we have a separate control block and IO, input output block, right? We provide some inputs, take out some output, and we control the flow of information between the memory block and the processor. Meaning, if you need to do some sort of multiplication, you fetch the data from the memory block, do that computation, and store the output maybe in the memory block again, unless you want to just directly show it at the output. Okay, and data path is made out of multiple segments. Like we have registers, we have adders, we have shifters, we have multiplexers. Depending on what you want to do, you bring in that memory and provide as input to maybe the adder, maybe the shifter, maybe the multiplier, maybe the register, depending on what you want to do with it. Okay, so all of this, obviously, this is a really high level simplistic view, but just to give you some perspective as to how this data path is made of. And here are some comments just to easily explain what these comments are. We typically do not deal with one bit at a time, right? Because that's going to take a lot of time to analyze the entire bit string. So we typically deal with a word level things, meaning 16 bits at a time. So we fetch 16 bits, process on top of them, and then store the output for those 16 bits. Okay? Just as an example, you can do 32, you can do 64, depending on how your algorithm and architecture is designed. But we don't typically do one bit at a time. Okay? That's not how things are done. So this is often known as bit sliced architecture. I mean, specific chunk of bits. If you don't have that many bits, maybe say if you have just 5-bit story about, the rest could be 0. The rest could be like, any default value that you choose to. Okay, so that's the boring slide. Let's get it out of the way. Here is where things become more familiar to us. Without going to this slide, if I give you a function, maybe think of a function, AB plus BC plus CA. Can you guys make a circuit, a CMOS logic circuit for this function? We can easily do it together, can we not? And please check out that supplementary document that I uploaded, okay? There you'll see an example like this, where when you have common terms into multiple sections, you can just take one of them out and simplify this a little bit. Okay, that makes things easier to implement. Does it make sense? Okay, just to keep in mind. So why did I tell you this? Because you see there is this same function sitting right here, AB, BC, and CA. What are these? Let's now get back to the drawing board again and try to add a couple of binary numbers. Maybe this too. Remember, we talked about it in one of the previous lectures. Let's try to add these numbers, okay? The first number could be A, the second number could be B, and the first bit of the first number is A0, A1, A2, A3, I mean in series, and then these numbers would be B0, B1, B2, B3. So just keep that in mind. Now, let me simplify this a little bit. Let's try to add these two numbers first, 1 and 1. So, I mean, binary addition. What should be the result when you add 1 and 1? 1, 0, right? So whatever you get corresponding to the same column as the digits that you're playing with is the sum. Okay, just keep that in mind. Or we just typically use S. And the extra bit that you will then provide to the next column is called carry. Or get used to the term C. Does it make sense? Sum and carry. So binary addition, you guys probably already know this. Now let's see what happens to the next stage. At the next stage, you already have a signal A, maybe A1, and you have B, B1, but you have one extra input coming from the previous stage, right? What is that? That is the carry in, input carry. Can anybody tell me what was the carry in for the first level? No, the first carry in. The carry in for the first level was like 0. We don't have to have any carry for the first level, but you can treat it like a carry. The carry input was 0. But for all the other levels, can you predict what's going to be the carry in? I mean, you don't know for sure whether it will be 0 or 1. That depends on what bit combinations you have in the previous stage. Am I making sense? For example, instead of 1 and 1, if you had 1 and 0, then you wouldn't have any carry at all, right? So my point is, can you think of each one of these blocks? Now, let's focus. Each one of these blocks as a processing unit that deals with 3 inputs. One is one of the bits of one of the numbers, the corresponding bit for the other number, and the carry in from the previous level. These are your 3 inputs. Am I making sense? Why did I choose to have this CI in a separate position than A and B? Because that's a different type of input. Remember, A and B are ready to go. You already know what A and B are going to be to start with, but you do not know what C is going to be. So it's a different type of input, which will have to wait for the previous state. So to distinguish that, we decided to just show it in a different way. And what's going to be your output? You have a sum and you have a carry out for the next stage. Make sense? Okay. So can I say that this tiny block that you see here, that's the adder block. You have A and B, 2 digits, 2 bits, by the way. And you have a carry in coming from the previous level. You have a carry out and sum. Make sense? So this is a logic function. This is a logic circuit that will have 2 outputs, carry and sum. All right, and 3 inputs, 3 input, 2 output. Okay, now truth table. Are you guys ready for it? It is a little bit difficult to explain, so please pay your full attention, because chances are if you understand this, your project will be super easy, and hopefully, I mean, you just surf through this lecture. So if you have any question, feel free to just stop me, and I'll be happy to go over it again. Now, we have a 3 input scenario. So this is the truth table for that 3 input scenario. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. As you know, the regular stuff, binary truth table. And how do we come up with these S and C values? Okay. Let me just show you one example. Let's do one addition ourselves. 1, 1, 1. Can you guys help me add these through 3 binary bits? Can you guys help me do that? 1 and 1 will give you 1, 0. And then when you add the other one, it will give you what? 1, 1, right? So your sum should be 1 and your carry should be 1 as well. So you see in the truth table, you have sum 1 and carry 1. That's how you come up with the truth table. You actually add it and see what you are supposed to get. Make sense? Let's try one more thing. Maybe this guy. 1, 1, 0. Let's add this thing. 1 and 1 will give you 1, 0, and the other 0 doesn't matter. So you have 0 here and 1 in the other side. So this is gonna be sum, this is gonna be carry. So can I say that my sum is 0 and carry is 1? Any problem? Okay. That's how we come up with this truth table. You don't have to memorize or anything. Now, given the truth table, you can, this is not a digital logic design course, but apparently, simply by using this truth table, you can easily figure out a logic function. I mean, I'm really tempted to show you how, in case you don't remember or you don't know. I don't know whether you guys have taken the DLD course, okay? Let's talk about the sum. Let's look at positions where you have a 1. Only the positions where you have a 1. Okay, in the sum section. Have I marked all of them? Okay, so sum would be wherever you have 0, take a prime. Wherever you have 1, take it as this. So you have 0, 0, 1 for A, B, C, right? So I will write A bar, B bar, Ci, because A was 0, B was 0. So A bar, B bar, and C was on 1 already. So as is. And let's go to the next row. Between multiple rows, we'll have a plus sign. Again, I'm not giving you the reason. It's not DLD course, but next one, A is 0, so you have A bar. B is 1, so you just have B. C is 0, so you have Ci bar. Make sense? Next row, plus. A is 1, B is 0, C is 0. Final one, A, B, C, because all of these are 1. Makes sense? So you see, you come up with this function. It's not random. We go through the DLD design process. Okay. Here is where our course should start. Given this function, oh, by the way, I forgot to do the same thing for C0, but I hope you guys can do that yourself, right? Using the same approach. Okay. Now, you have 2 expressions, one for the sum, one for the carry. And by the way, although it looks really, random, but it is not. Turns out this tiny function is nothing but a 3-input XOR gate. Okay. There is something interesting about XOR gate. A, B, 0, 0, 0, 1, 1, 0, 1, 1. Let's check it out. 0, 0, 1, 1. You know that this is the truth table for an XOR function, right? And XOR is nothing. This expression is XOR. And get used to this. An XOR function is AB bar plus A bar B. Okay. But let's forget about all of these expressions and try to make sense of this in a realistic scenario. You see, whenever both of these bits are the same, like either 0, 0 or 1, 1, your XOR output is 0. You see? And whenever they're different, there is another term for being different. Can I say exclusive? Can I say that these 2 inputs are exclusive? Right? Then your output is 1. So XOR or exclusive OR is only 1 when the inputs are exclusive, right? That's why the name. I mean, just to make you guys interested in it. When it comes down to a simple logic circuit, nobody cares. Okay, just one of these logic circuits. But had I told you that XOR logic is used in data centers like Google and Facebook and Microsoft, all those big data centers, to check the integrity of the stored data. How is that? This, big companies always have backups of backups, right? How should they compare their stored data in one backup versus the real data and make sure nothing is being changed unintentionally? They do a really simple computation, right? They do bitwise XOR. Take 1 bit of stored data. Memories have a location. Let me just write something here. 1001, 1110. Let's think of a 4x4 memory array, right? Again, we haven't gone through the memory array, but that's okay. 4x4 memory array. If I ask you the location of this guy, can anybody help me find that location? Can you not use your row number? Row 2, column 3. Can you not do that? So data is stored in a matrix format in a memory array. So it's easy for us to figure out the location. So when you copy the data somewhere else, maybe the same data somewhere else, you can easily figure out the location that you want to compare it against. You're not going to compare this with any random data, right? So you take the data from this given location, row 2, column 3, and you take the same location data from the real memory, and you do a bitwise XOR. And what do you expect? If these are exclusive, you see the point? Exclusive, meaning if these are different, then maybe an LED will light up. because you have a 1 in the output. Otherwise, nothing, no action. So you keep XORing these two blocks and you don't see anything. The moment you see something lighting up, oh man, something's wrong. You have exclusive data in the same location. Am I making sense? So you take the data, you take its copy, you do an XOR. The XOR should always be 0. The moment the XOR ends up not being 0, you have a problem. Make sense? So just one example as to why you should care about XOR gate. Okay. Anyways, sum function is nothing but a 3-input XOR gate. Yeah, let's see whether that makes sense to us. Let's look at whenever this sum function is 1. Okay, make sense? What does 3-input XOR mean? Let's try to make sense of it. Let's just mark these things down first. You see, whenever you have an odd number of similarity, for example, you have 2 zeros, odd number of 1, like in terms of parity. Let me just, yep, right here. You see, whenever you have odd number of 1, like just 1 high, or just one or 3, your output goes high. Okay. Again, just to make sense of what it means physically to be a 3-input XOR versus 2-input XOR. But you don't have to worry about any of this. Just worry about this expression. And I'm happy for this course. Same applies to the carry output. Okay. Now, with that in mind, we will come back to these things later on. And this block later on. Let's just stick to this basic sum and carry and go to the next level. We'll come back to this again. Don't worry. Here, let's see the circuit first. Okay, we're ready to see the circuit. Please, be attentive as much as you can so that we can go through this circuit very easily. This is a more complicated circuit, of course, than the other ones that we went through. You see that this carry function is something that we already noticed in the previous slide, and this sum function is somewhat different because they have performed some Boolean computation to make it a little bit easier to implement. Am I making sense? Basically, if you just multiply this, you'll get back whatever you had before. Okay. So this is a simplistic expression for the sum function. So sum function and carry function. Let's try to implement that. Let's do it together again. Okay. Online folks, please pay as much attention as you can and ask me questions if you have any. Okay. Let's first implement the carry function, which is in the red zone. So AB, BC, AC. AC, BC. You see that? Do you see what changed here? Yes, thank you. So let me just, again, I wish you had already looked at the supplementary document that I uploaded, but if you haven't, please do, maybe after today's class. So we can easily simplify this expression further by taking the CI common. Okay, so you have just one CI and A plus B. So can I implement that? A plus B is 2 parallel transistors and CI in series with it. And then AB means A and B transistors in series. And then you have a plus between. So you have both of them in parallel. Does that make sense as far as our training goes in terms of CMOS circuit design? So we have successfully implemented this portion with NMOSes. What should I do with PMOSes? Just, make complementary. For example, A and B were in series. So we will make them parallel. See that? These A and B were in parallel. So I've made them in series, and this CI was in series with them. So now it's in parallel with them. Okay. And this both branches, let me just use a different color. This branch and the other branch A and B were in parallel with each other. But now they are going to be in series with each other. Make sense? If you're confused, please first go through that supplementary document that I uploaded. Okay, this is really important and things will make a lot of sense. So I hope based on our training so far, we all understand what this thing is. There is one thing that's missing. Have we implemented C0, C out? Have we implemented C out already? What have we implemented? C out? Not. So that's why you have a inverter in the output to get C out. So this is nothing but C out bar. And then you have C out. Okay. Now, this is your carry portion. There is nothing new. See, that's the reason why I wanted to start with this discussion, because it's so much related to what we discussed already. Now, take a look at the sum function, will you? The sum function. In a sum function, you have A, B, and Ci, but you also have C out. By the way, this is a modified sum function. This is not the exact sum function as you saw here. Okay, so people came up with an intelligent way to merge this C out with sum. Right? I haven't shown you the Boolean computation here, but they have gone through the math and they simplified it, and they came up with a way to reuse this carry output. Why? Because they realized you will anyways have to calculate C out bar, because you're getting it for free right here. If you could somehow reuse that and simplify your circuit, that will be, better, of course. And that's exactly what they did. Okay, so we will be implementing this portion here, right here, in this section. Okay, so let's try to make sense of it. A plus B plus C. Do you see that? A, B, C in parallel. And you have a C out bar in series. This is nothing. What was this guy? C out bar. The C out bar is in series with it. Does that make sense? Okay. And then ABC were in series. So you have A, B, C in series. And then there was a plus in between. That's why they are parallel. And by the way, this is ground. This is also ground. So they're essentially parallel. Hey, are you guys confused or are you okay? So we have managed to do that for NMOS branches. We can surely just revert this for the PMOS. So I'm not going to go through this again. You just, make the series connections parallel connection series. Done. You get the PMOS branch. Okay. And by the way, don't forget our popular CMOS inverter to get sum out of sum bar. Okay. Same problem. Okay. Few take-home messages. If you count the transistors, you have 28 transistors. To add what? One bit with another bit. 28 transistors, right? You see that? Right? See, here is how there are different paradigms of research. Okay. What you are learning today in classroom was research material, maybe 10, 20, not 10, 20, like 40 years ago. Okay. People come up with a basic design, which works, like this one. This design works. It was the cutting edge at some point. Then people started realizing, hey, there is one problem with this design. Can we solve it somehow? Okay. What do you think, professors like myself do all day? We try to figure out problems and limitations in existing, solutions. Oh, you have an iPhone? Do you need a better iPhone? You don't need a better, no, you need a better iPhone. I will give you a better iPhone. You'll have to have a better iPhone. See the point? Even if you need it or not, we will figure out a problem with the existing solution and come up with something. See the point? Otherwise, you don't have a new product for the future. Imagine, think of the virtual reality that Meta, Facebook is coming up with, right? We hardly ever finish exploring our own reality. Like, how many countries have you visited? Just imagine. But now we are trying to come up with ways to kind of take you to a place that's a fantasy or something, right? Yeah. The thing is, you didn't need it, but be sure that within the next 10 years or so, for the next generation, this will be a necessity, right? Hey, I don't have, my friend has it. Right? When I was a student, like when I was in my, not undergrad, when I was in high school, I used to think that cell phones are luxury. Only the very rich people will have cell phones with them. Otherwise, you're all going to be using wired phone, right? Even at some point when I was a kid, wired phone was more like a luxury in my home country. Anyways, not anymore. I mean, now everybody has smartphone or anything, stuff like that. So something that's not a necessity now will become a necessity later. So people identify problems in the designs that are already working and come up with ways to make things better. Okay, it's not always useless, meaning they don't just invent problems and solve problems always. There are genuine problems in many scenarios, like this one. Imagine if we didn't have good addition capability, all of the advancements that we have had in modern electronics. I mean, just think of this trivial circuit, an adder, which we're learning as part of a VLSI course. It's not quantum physics course or anything that changes the world, right? It's a really, benign circuit course. But if you hadn't have these adder circuits in a better condition, then our computers will not have as much good performance, not even nearly close. Okay, and then your capabilities to simulate and emulate and compute stuff will be really limited. Now you can send rockets to maybe Mars. Who does the calculation? The computers. You don't do calculations by hand. And by the way, trust me, there was a time where people used to do hand calculations. I've seen a documentary where, it's true. I mean, they used to come up with charts with computation. And if you make one mistake, one digit here and there, you can just imagine what's going to happen, right? You lose billions of dollars. So you need extremely high accuracy, right? So this progress in computing power is directly linked to the progress in all other fields. Drug discovery, if you think of, just imagine, a new medicine that's coming up. You just expect the biochemist or medical scientist to come up with a solution to any disease that shows up. Hey, why haven't they figured out diabetes yet? I will just, drink a bunch of Coca-Cola and never have diabetes. I mean, that could have been the dream, right? But it's not there yet. People are still getting diabetes. Why aren't they being able to speed things up? People don't just randomly come up with a way that, hey, here is a medicine, just take it and you'll be fine. They do a bunch of simulation, and these are extremely complicated ones, more complicated than we can even imagine. And to be very precise, we don't even have, with all of our powerful supercomputers, we don't have the capability to even simulate a caffeine molecule for coffee. Caffeine molecule, just imagine. We don't have the capability yet. One of the biggest selling points for quantum computers for next generation is that it will allow you to simulate caffeine molecule. I mean, just as an example, something that people can relate to. Hexamethyl benzene, nobody knows. Caffeine, yeah, I know that. Yeah, I know caffeine. Although you haven't really seen the, formula for caffeine. I mean, it's not the real name. It's not the chemical name or anything, right? Anyways, the fact is, simulating complex molecule could be reality. I didn't mean to take the tangent unless to show you the need to further improve a circuit to make our capabilities better. Okay? Now, that's why people do research, to solve problems. So before solving problem, you'll have to first identify the problems, right? I see a bunch of problems in this circuit. To start with, let me point out this one. You have a bunch of transistors in series with each other. 1, 2, 3, 4 PMOSes in series with each other. Do you guys remember the problem with series connected transistors? Right? Not only rise time, rise time is, yes, you're right. Propagation delay in general, right? In general, you have a bunch of capacitors which will have to gradually charge and discharge when you have a bunch of series transistors. Remember intermediate nodes? I hope you guys do. All right. You also have series connected transistors here, but that's not the worst case scenario. The worst case scenario is this one, where you have 4 transistors in series, which is a really bad thing. And 28 transistors certainly is a lot of transistors. And there are other things that I haven't pointed out yet, but I will in the next slide. So, but here you have a circuit, an adder circuit that works. Good news, that works. Can anybody tell me any other problem with having so many transistors in series? Thank you. Yes, I was gonna draw this CMOS inverter to remind you guys, 1, 2, say. to balance this circuit, you have to have like 3, 3, 3 here in the NMOS. And you should start with 2, 2, 2, 2, but then you'll have to multiply it 4. So you have 8 times the width for each one of these PMOSes. If that doesn't mean anything, that means you haven't gone through the previous lecture properly. Okay, please do. And please also see the supplementary document. I have a bunch of these circuits worked out there. So you have a huge, space requirement just to add 1 bit. Can you imagine, right? Just try opening up a text file. That will easily be more than a kilobit, meaning thousands of bits. And you need 28 transistors, huge sizes for each one of these PMOSes to add 1 bit. This is unimaginable if you think about it, right? That's why we need billions of transistors and trillions of transistors. Okay. People started coming up with unique ideas to make it simpler. And by the way, I have kind of skipped one idea already. Remember, reshaping this sum function to incorporate Cout was a first step towards simplifying. So you are looking at a simplified version. The previous version was even more plain vanilla. What's the previous version? Try implementing this at home. Just implement this equation, this function. Simple, plain vanilla function. That's the simplest solution. Okay, and this is a little bit more involved, where we reuse the output, carry output. Okay, now, you guys ready for it? Sorry, I'm going back and forth because I just want to make sure that things are kind of related to each other. Now, I skipped this slide, but I have just come back to this because of this reason. 1101, 1111. When you add, maybe when you add these two numbers, 2 bits, you get a sum, and then you provide a carry to the previous one. And then you compute this, provide carry to the next one, and compute this, provide carry to the next one. Doesn't that look like a chain? You see, when you add a couple of bits, you have to connect the output to the next stage, and the output of that stage to the next stage, right? And so on. Does that make sense? Which output do you need to carry? Do you need to connect? Do you need to connect the sum output or the carry output? And remember, I just told you that we have 2 outputs. We have carry output and we have the sum, right? This circuit provides 2 outputs, sum and carry out. Which one of these 2 output ports should I connect to the next stage? Yes, thank you. Because we don't provide the sum to anybody. I don't know if this is visible enough. Just one more time. When you add, you get a sum, and that sum remains there. Only the carry is given to the next stage. And that stage will do some computation and give you a sum, and the carry will be given to the next stage. So we should only connect the carry out to the next stage, not the sum. The sum remains independent. So here is what it is. A0, B0, remember the first bit, the second bit, third bit, fourth bit. This is the initial carry. Initial carry. This is the sum. And this is the carry output for the first stage. Make sense? And you see the carry out for the first stage is the carry in for the next stage. Do you see that? And the carry out for the second stage is the carry in for the third stage, and so on. Right? Let's draw it the other way. I mean, I don't know, this is taken from a textbook. That's why they're doing from left to right. But we don't typically do that in real addition, right? In real addition, we go from right to left, right? LSB to MSB. So let's try to reshape this in that way. Can we work together on this? Let's start with A0, B0, the very first bit. This is A0, this is B0. What's going to be my carry in? Carry in 0 for the first stage. Yeah, there is no carry. So carry is 0 for the first stage. But you still have a pin. So you get some 0. And then you'll get a carry out from this. And that carry will be given to the next stage, which will be adding A1 and B1. And this carry out from this guy will be the carry in for the next guy. And you have a sum output and you have a carry. Make sense? Are you guys confused or not? And so on. And so on. Done. Okay. So the adder structure that I've just drawn, okay, this is called a ripple carry adder. It's as if, let me just draw something. Okay, ready for it? Picasso. Anyway, the carry is going to be rippling through this chain of circuit. Carry is going to be rippling through this chain of circuit. That's why it's called a ripple carry adder. I mean, that's a nice name. I mean, that they came up with. Okay, does that make sense? This is that, it's otherwise known as RCA, ripple carry adder, highly used in many applications in real life. This is the adder that you are gonna implement in your course. Okay, course project. By the way, you guys have been working on NOR gate design. 2 NMOSes, 2 PMOSes. Lab 5 will have you work on NAND gate design. So 2 NMOSes in series, 2 PMOSes in parallel. I know I'm drawing it really roughly, but the point is, you see, you have been dealing with this type of circuits. The only thing that you are now gonna do is what? Add bunch of NMOSes, bunch of other PMOSes, done. That's it. You see, is this fundamentally any different? Instead of dealing with like 2 NMOS, 2 PMOS, now you'll be dealing with 14 NMOSes, 14 PMOSes, maybe. I don't know. But it's all the same thing. The schematic, I mean, for this one, I don't know how much it takes you to connect all these transistors, right? If it takes you like an hour, that should take you an hour and 20 minutes, probably. A few more transistors. Because all the other steps remain the same, if you think about it. Make sense? Imagine, when you come up, can I get all of your attention for a second? You see, when you have this circuit, can you help me write a block diagram for this circuit? Let me draw it right here. You have 2 inputs, A and B. A and B. And one more input. What is that? CI. So you have 3 inputs. And you have 2 outputs. See? You have carry out and you have sum. What do you have here? What is this circuit? The adder. You have an adder right here, right? And if I ask you to make a 8-bit adder, what do? Do you make this 8 times? You just make one. And then how many of you know how to copy paste? Like copy, paste, drag and connect. You see the point? So even if I ask you to make like 88-bit adder, doesn't matter. Just copy it 88 times. That's it. All you have to do is design this once. Done. Okay? So I hope that makes sense. And we'll be here to help you out if you ever feel confused. Okay. Now, the point that I try to make is this is how the chain looks like. There is one other information that I haven't given you, but you have to listen to me carefully to understand this. This is a simple expression that motivates many other work in adder design. The delay of an adder operation, okay? Let's try to delay that we have to incur to complete this addition operation. This is a 4-bit adder, by the way. Imagine that it takes T carry amount of time to generate the carry in one stage, right? Let's consider that each one of these stages take a specific amount of time. Forget about this. T amount of time to create a carry. Okay, so can I name it T carry? Just to make it easy to understand. So how much time will the next stage take? Same for the next stage, right? Any problem so far? So imagine starting from this point to the other point, how much delay will I have to incur? 1 T carry, 2 T carry, 3 T carries. So can I write 3 T carries to reach this stage? Can I say that? And then, by the way, we are defining the delay as the time it takes to get the final sum. Let's see. Maybe you know the answer for S0, which is 0. S1 is 1. S2 is 1. Say, maybe this is also 1. But S3 hasn't arrived yet. Do you know the full answer yet? No. Who are you working on? Oh, sorry, waiting on. You are waiting on S3. The moment S3 arrives, oh, done. Addition complete, right? So you just define your addition delay in terms of the delay that you incur to finalize the value for S3 or S4 or whatever is the last bit. That will define your delay. Now see, now you are at this point. How much delay have you already incurred? 3 times T carry. Make sense? 3 times T carry. And then afterwards, let's consider that one stage takes T sum to calculate the sum. Make sense? Let me simplify. Let's characterize a block. Sum, carry output, carry in, A, B. Let's consider that each one of these blocks has 2 characteristics delay. Sum delay and carry delay. What does sum delay mean? The amount of time it takes to compute the sum. And what is carry delay? The amount of time it takes to create the carry. Make sense? Are they going to be same or different? Can anybody tell me? Why different? Because you see, you first create the carry and then you use the carry to calculate the sum. So they're not going to appear at the same time. Make sense? There will be a delay, obviously. Okay, now, having said that, remember two terms, T carry and T sum. Okay, let's try to make sense of this equation now. Let's see how much time it takes for us to get the final addition, S3. You have to go through 1 carry stage, 2 carry, 3 carry. Is ready? And finally, you need to go for a sum stage to get S3. So for a 4-bit adder, you need to have 3 T carries plus 1 T sum. Can I say that? How about a 5-bit adder? 4 T carry, 1 T sum. So if you have n-bit adder, imagine you have how much? N minus 1 T carry and 1 T sum. Make sense? Can you guys see that the sum delay is least of our concern? What should be the most of our concern? The carry delay. If we could somehow reduce the delay for carry, things will be much better, right? Imagine you have a 64-bit adder, 63 times T carry and 1 sum. Who cares about sum delay, right? Just care about the carry delay, reduce the carry delay, and you'll be in good shape. Am I making sense? So that's what motivated many other research work moving forward, which I will show you right now. I will just show you this one other circuit diagram, and then okay, let's just go through this first. Better structure, a mirror adder. Some researcher in some university thought about, hey man, so okay, that's what's limiting the delay, right? The carry delay. What can we do to reduce the carry delay, right? Let's think like that researcher. Okay, let's first identify the sources of carry delay. Let's first identify the sources of that. Let's ready for it. This particular node has a bunch of capacitors. Remember, capacitors are determining factor for delay. The more capacitor you have somewhere, the more delay will there be. Let's see how many capacitors is it driving? You guys ready for it? I hope. How many of you remember that transistors have drain capacitance, source capacitance, gate capacitance, right? So as many terminals you have connected at a given node, you have that many capacitors. So you have capacitance component coming from the drain, source terminals of this NMOS and PMOS. And here is another, 4. Get used to this term. In circuit design, whenever you have capacitors coming out of drain or source, we call it the diffusion capacitance. Make sense? Diffusion capacitance. And gate capacitance is called gate capacitance. Done. Make sense? Any problem? Okay. So you have 4 diffusion capacitances. And you have gate capacitance from the PMOS, gate capacitance from the NMOS, all connected to this node X. And then you have more gate capacitance from this PMOS, more gate capacitance from this NMOS. Oh man, I mean, you're literally loaded with capacitors at this node, right? So they figured out, can we somehow reduce this capacitors? To the moment you reduce capacitance, things become faster. Okay, and get used to this. The more severe of all of these capacitive components, you have 4 diffusion capacitances and 4 gate capacitances. Remember, gate capacitance is always higher. Gate capacitance is the killer. Make sense? If you could reduce 1 gate capacitance, that has a huge impact. Okay, that's what got them started on, a new direction. Here is that idea. Inversion property. What is it? In a logic function, in a Boolean logic, you have A, B, and C as input, some output, carry out. If you just invert the inputs, meaning instead of A, B, and C, if you provide A bar, B bar, and C bar. Make sense? Instead of A, B, and C, if you just provide A bar, B bar, C bar, you will get sum bar and carry bar. Make sense? So in simple plain word, if you invert the inputs, the outputs will be inverted. Done. Okay, simple. And that's what is, I mean, this is taken from a textbook again. They, instead of using bar, they have used these circles to show that you have inverted inputs and inverted outputs. Does that make sense? Essentially, I like the other one better. You have A bar, B bar, C bar. So you have to get sum bar and carry bar. Done. Okay, make sense? Now, what's the big deal? The big deal here is, let's take a look at this circuit. Here, you already had carry bar, carry out bar, but there was no one to use that, for the next stage. For the next stage, you need the carry out, not carry out bar, right? But if there were someone who could just take C out bar and not worry about C out, we could have saved this extra inverter, couldn't we? Just imagine if your next level were fine with carry out bar, you would have been okay with getting rid of this inverter. Am I making sense? Let's do exactly that. See, here is a scenario. You start with a regular adder that you know, A, B, and carry in. You get some output, carry output. Notice one thing. Why is the carry inverted? Whenever you see this circle, you will realize it has been inverted. Why is it inverted? Anyone? Because, CMOS. But in a regular circuit, we use this inverter. But we have decided to get rid of this inverter now. Okay? So when you get rid of this inverter, you are left with this carry out bar. Make sense? That's why you have this. Let me show you. Let me just point out. See, this carry output is inverted. That's why you have a circle. Because we have gotten rid of inverter. No inverter at C out, carry out bar. That's why you are getting an inverted signal, like the CMOS circuit. Any CMOS circuit will give you inverted output. Make sense? Now, how can you make use of it directly in the next level? Any idea? You see, Now that you're getting C out as invert, why don't you invert A and B as well? Then what are you gonna get? Anyone? Anyone? Yeah. So remember this one. When you invert A, B, and C, your sum and carry will also be inverted. Make sense? So when you have inverted carry, inverted A, inverted B, your sum and carry will also be inverted, right? But remember, you design this circuit in a way that had this been carry out A and B, then you could have gotten sum and carry, right? Let me just draw with 2. Even I'm getting confused trying to explain this. Okay, see, carry in. Get ready for it. A, B, you have sum and carry out. Notice you have an inverter here. And you also had an inverter at the output. Remember that, right? You had an inverter at the output. Don't forget that. You also have an inverter. Okay. Now, the moment you change this, like get rid of this inverter, you end up getting C0 bar. Okay. We'll see how to connect that to the next level. But before we connect it, let's see the next level. You have A1, B1, carry 1. The output should be sum 1 and carry 2. The next level. Okay, makes sense. Now, when you get rid of this, forget about getting it. When I invert all of these inputs, what do you expect? Inverted outputs. You should expect inverted outputs, right? No problem, I hope. Remember, this guy also has an inverter. This guy also has an inverter, right? I haven't gotten rid of that inverter yet. The moment I get rid of that inverter, this inverted output will get back to what? C2, normal. You see the point? I hope it is making sense. I know it's really a little bit confusing, but should I go over it again? So you had C out and you had an inverter at the output. The moment you get rid of that inverter, you end up getting C out bar. And you provide that C out bar as an input. And you also invert A bar and B bar. So you should get an inverted output at the carry. But then you also get rid of that inverter. Like you get rid of any inverter at any of these outputs, right? So you have invert of invert, meaning you actually have C2. Make sense? Okay. So where is it? Yeah, right here. So that's why you have regular carry instead of inverted carry. But the sum remains inverted. Make sense? Did it make sense? Did it? Did you notice that the sum will be inverted and it remains inverted because we didn't change anything to the sum. We only gotten rid of the carry. Make sense? Okay. So apparently, you see these zones are grayed out because they are using inverted inputs and the other ones are using non-inverted inputs. By doing so, you are introducing 2 different types of cells. You are incorporating cells that take in the real inputs, incorporating the cells that take in inverted inputs. Does that make sense at all? And which principle have you used to achieve that? Inversion property. When you invert the inputs and all the outputs will be inverted. That's the inversion property, right?
Why are we doing this? Can anybody remind me why have we decided to do this? All because of this simple insight that carry will determine the overall performance. And if we could reduce the carry delay, that would have been really impactful. And how are we managing to reduce the carry delay? By getting rid of this extra inverter at the carry. Make sense? And how are we getting rid of this extra inverter? By making use of this inversion property, right? So you have odd cell and even cell, odd cell and even cell. So do you see any concern here? Are we, you know, reducing the number of inverters required in the overall design? Anyone? Are we reducing the number of inverters required in the overall design? We are actually increasing the number of inverters, if you think about it. How many of you can tell me why? Anyone? Thank you. Yes, you are taking out one inverter out of the carry portion, but you are adding in, I mean, you are getting A1 and B1. Then you'll have to convert them into A1 bar and B1 bar, and so on, right? So for each stage that you're taking out an inverter from, you're adding two other inverters to invert the inputs. Oh man, I mean, you are losing out in terms of area, of course, but what are you gaining? Can you imagine? You are simply reducing the delay for the carry. Why? Why? We imagine A and B. A and B are always available. How much time will it take? A few picoseconds maybe to invert that. But the carry propagation is the killer. So if you can, you know, speed up the carry propagation, that will lead to the overall performance. Am I making sense? Making sense? So we don't care. That's the reason why I wanted to go over this expression. Where was it? Yeah, this expression, to show you how important it is for us to reduce the carry delay. That we are willing to introduce more inverter simply to reduce the carry delay. To move one inverter from one place, add two more inverters somewhere else, simply to reduce that carry delay, right? Okay, so if you get that, this is the next step. This is another better design that somebody else came up with. See, so that was a nice approach, and they got a paper out. Oh, here is our approach. Here is what you can do. You know, people started making, like the company started making adders using this approach and saved, like improved the performance quite a bit. And then somebody came up with, oh man, this was a low hanging fruit. We could have thought about it. Somebody has already published. What can we do now? They have to come up with something more ingenious. Okay. And here is what it is. Let me use a different color here. Can any forget about the PMOS branch? Don't look at the PMOS branch yet, okay? Please don't. Just look at the NMOS branch now. Can anybody help me identify this NMOS branch? AB, BC plus AC. You see that? Why do you have one C? Because we have taken this C as common, right? Why do you guys look so confused? Is it not the same, exactly the same as the previous one? You see, is it not exactly the same as the previous one? And take a look at this portion in the sum section. Did anything change there? Anything? Exactly the same. Then why am I claiming that this is better? These are exactly the same thing. Now, take a look at the PMOS branch. Do you see any problem? Yes, it is mirrored. Yes, that's why the name mirror adder. But the PMOS branches in CMOS circuits should be complementary to the NMOS branch. Like whenever you have series connection, PMOSs should be in parallel and vice versa. But they are not for this circuit. Why? And how is it even working, right? I'll show you. So they have used something called the self-duality property of sum and carry function. It's kind of like a lucky coincidence. I mean, not really, I mean, yeah, maybe lucky coincidence, okay? A few functions in Boolean algebra has this property. Let me show you what I mean. Let's think of a function. AB plus BC plus AC. I mean, I was going to tell you that this is nothing but your carry function. Remember? I mean, okay. Imagine when I say that we will convert the series to parallel, parallel to series, what are we actually doing? We are converting these products into sum and the sums into product. If you think about it, aren't we? Yeah. Let's do that here. Let's like complementary. Let's do that. Let's convert this product into sum. So AB becomes A plus B and sum will become product. Can I do that? So making this complementary means to convert this product into sum and sum into product. Okay? Can we work on this math together, like in a second, in 30 seconds? Let's multiply these two. AB, ACI. B and B is what? Just B. BCI times A plus CI. Okay, let's go through this again. AB times A is what? AB. You know that, right? A and A means A. ABCI. ACI plus A. I know it's taking a while, but I hope it's going to be worth it. Okay. So you'll see, I should have started with this. I don't know. I'm running out of space here. But you see, you have ACI, you have AB, you have BCI, right? Any problem so far? Okay, I haven't taken the complement though. So meaning, actually, let me start with a small function. Sorry about the confusion. AB plus BC, let's do that. If you do A plus B times B plus C, you'll get AB plus AC plus B plus BC. Okay. Now, if you, this is say the complement of it. If you take bar of this bar, you have to do AB plus AC plus B plus BC whole bar. Okay. Then if for some reason you get back this exact same function, then we will say that this function is a self-dual, meaning its complement and regular form will give you the exact same thing. Am I making sense? So if you take a function, take its complement, after all those computation, I mean, this is going to be, maybe I can upload a separate supplementary document to show you the full calculation in case you're interested, and I'll do that, no worries. But considering time and space, let me just give you the final picture. If you take the complement of a function and you get the exact same function back, it's called self-dual. Am I making sense? So there are some functions, some Boolean functions that are self-dual. Turns out the function that you had, I mean, of course, it's going to take a while for us to calculate that. But this function, if you take bar of this function and go through the calculation, it's going to be exact same thing. After all those, addition and taking things in common and doing some Boolean computation, it will all come down to the same function. Make sense? So somebody noticed that this sum and carry functions are self-dual. And based on that assumption, if they're self-dual, what's the point in changing the type? Why don't you use the exact same function on the other side? Am I making sense? This is unique for what? Sum and carry function. That's why I told you that this is kind of like a lucky coincidence. Had it not been the case, we wouldn't have the luxury to use a mirror kind of scenario. Am I making sense? Okay, so that's why you see this branch and that branch are exactly the same as the inmost branches. Okay, got it? Any problems so far? Why have we managed to do that? Because of the self-duality of sum and carry functions. And I'll do the full computation, don't worry, and I'll upload a supplementary document, okay, for the interest of time and especially space. Okay, now, there are many benefits for, many benefits to this mirror adder scenario. First of it would be, you see, you just have 2 transistors in series here, and you have 3 transistors max. You don't have 4 transistors in series like the previous case. Remember, you had 4 transistors, but now you just have 3 max. Isn't that better? First of all, that is the biggest selling point, that you are reducing the number of series connected. See, you had 4 transistors in series before, but simply by making this thing self-dual, but using the self-duality property, you're managing to reduce that load. And by the way, that doesn't mean, oh, just 1 transistor. Remember the sizing for transistor? I mean, I'm just going to show you the numbers here. 6, 6, 6. Instead of 8, 8, 8, 8, you now have 6, 6, 6 times width. So you're reducing the area quite a lot. In Cadence, in your layout, try doubling the area of a PMOS and see how it looks compared to the NMOS. It's going to be like one tiny NMOS, a giant PMOS, spending and wasting a huge amount of area, by the way, because you cannot do anything about the other area. The NMOS will be tiny, the PMOS will be huge, right? So then you'll appreciate what it means to go from 8 to 6. You can visibly see, oh man, it reduces the size quite a bit. Okay, so that is the biggest selling point. Not just 1 transistor. It sounds trivial. 1 transistor and reducing the size of all of them. And I'm not even mentioning the delay improvement here, of course. Okay. There is another important. When you have symmetric NMOS and PMOS branches, you can easily make layouts. I mean, you will have to do the layout to appreciate that, because the PMOSes and NMOSes are exactly identical. You can have 1 vertical line connecting them, like parallel gate connection. I don't know if I'm making sense at all. So you have bunch of NMOSes and you have bunch of PMOSes. You have 1 gate with A, 1 gate with B. You see the point? Like, you can easily share these gates if they're symmetric. The reason why we are not always able to do that is because sometimes the NMOSes are in series and the PMOSes are in parallel. So, I mean, they're in different positions quite often. It's not so easy for us to vertically share this, right? You have to bend the lines and, do something with it. But that's another benefit that they claimed in their paper. But regardless, this is interesting enough. Hey, the first guy who came up with that circuit thought, hey, why didn't I think about this? Yeah, maybe because you didn't know about self-dual functions. Right now, somebody thought about it. Don't you think that if you guys were there, you would have thought about it? I mean, I feel that every time. I mean, okay, it makes sense, right? I mean, some theory that somebody came up with and got a Nobel Prize for, we thought, okay, we could have thought about it. Einstein got Nobel Prize for photoelectric effect, right? Photon comes in, photon hits the electrons come out of metals. Done. I mean, have you thought about this theory? How simple is it? Okay, something hitting something, something coming out. Okay, I deserve a Nobel Prize, I guess. Maybe. But sometimes, I mean, that's the case. When somebody comes up with an idea, it sounds easy for us. But anyways, just to guide you through these comments so that you don't get confused later on, let me help you navigate these numbers. The capacitance at node C0 is composed of 4 diffusion capacitances. Let's go to the previous slide. What is C0? This is C0. What do they mean by 4 diffusion capacitance? Let's make sense of it. You have 1 capacitance coming out of this, one capacitance coming out of this node. Where are the other two? Where are the other two diffusion capacitors? Right here. You see the point? Drain and source connections bring in capacitors. Those are diffusion capacitance. Less of a concern, by the way. More concerns would be gate capacitance. Let's see. Two internal gate capacitance. Two internal gate capacitance. What do we mean by that? There is a gate capacitance right here from the PMOS. There is another gate capacitance from the NMOS. And they're internal to this cell. That's why internal gate capacitance, right? You have 2, you have 4. Does that make sense so far? Folks, any problem? Finally, 6 gate capacitance in the connecting adder cell. What does that mean? Connecting adder cell. How is that possible? 6 gate capacitance, man, that's huge. Can you imagine 6 gate capacitance? How is that possible? Can anybody tell me? This is the tricky part. Look for 6 gate capacitance for the cell that will be connected to it. Let me just draw this. C in sum, AB. This is going to be carry out. No, I mean, just think of this. Can anybody tell me where this CI signal will be coming from? Let me just mark this here, okay? This CI signal, right? Can anybody tell me where will this CI signal come from? Yes, this is carry input for this guy, but this is actually going to come from the carry output for the previous guy. Am I making sense? So the carry out terminal will actually be connected to the carry in for the next stage. Make sense? So wherever you see carry in, this carry in will actually be connected to this node from the next block. Do you see the point? So how many transistors are you driving with carry in? One transistor, and you're driving the gate. You see, you're driving the gate with the carry. 1, 2, 3, 4. And this guy is the boss, is driving 2, 5, 6. See, 6 gate capacitances are being driven by this simple node. 6 gate capacitances for the next stage. Now, do you see the concern? I mean, folks, how many of you remember transmission gate? Just to give you a really quick reminder, we used an NMOS transistor and a PMOS transistor in parallel with each other, right? And they were, say, for example, if you have A, you should have A bar right here. So both of them will be on at the same time or off at the same time. If A equals 0, NMOS is off, PMOS is also off. If A equals 1, NMOS is on, PMOS is also on, right? So why do we have parallel connected transistors? Because NMOS can pass 0 quite well, and PMOS can pass VDD quite well. So we use their collective strength to pass any signal that we might encounter. Make sense? Okay. And I told you, let me see, try to remind yourself that we discussed a transmission gate-based XOR design. And if you don't remember how that looked, this is how it looked like. So I have that slide copied here. This is a review, as you see. It's not new. We explained this design with a truth table. Remember? This was the inverter that sometimes works as an inverter, sometimes doesn't. Doesn't ring any bell at all. We just discussed this in the last class. Okay. So the reason I'm telling you this is because I'm not going to explain this again for the interest of time. And the other reason is all of these are recorded. So I don't want to make you listen to the same thing over and over again. Okay. So this is a transmission gate based XOR. This is an adder circuit. which doesn't look like anything that we have seen so far, doesn't look like the CMOS circuit, you will appreciate the CMOS design style even more as you go through these alternative design principles and design rules, because they are so diverse and so difficult to understand compared to the CMOS circuits. Okay. All right. I'm not gonna describe this in full detail. I don't want to bore you. And the other reason is it's not really important for you, considering the cutting edge. Okay, we're not going to use this anyways. We're going to use the CMOS approaches, right? So without spending time and boring you guys, I'm just going to give you some hints, and I'll be more than happy to go over the detail if any of you are willing to dig deeper into this. Otherwise, just, to let you know that this is another alternative topology, which people proposed using transmission gates. And how does that come into being? That's where all those other things that we skipped right here will come into play. So computer scientists, not computer engineers, they look at these binary truth tables and they try to figure out patterns. Okay. Remember, we didn't talk about this column at all. For a circuit designer, this truth table will suffice. We can always come up with logic using this. How many of you have taken DLD, digital logic design? Do you know how to make a function looking at this ones and zeros, right? You just look at ones and come up with something, or zeros and come up with something, right? This is easy for us to do. We don't have to know the hidden pattern inside data, but computer scientists like to see hidden patterns in data. And that's what they did here. They noticed that, hey, depending on what happens to A, B, and C, you have three scenarios. You either generate a carry, you either delete a carry, or you either propagate a carry. I'm not going to explain all this reasoning, just going to explain maybe two. Delete a carry. Imagine, say you had a carry generated already. You had a carry, 1, but that carry was deleted at the output. Again, you had a carry. I mean, they are defining it in a way that this was also deleted. When does that happen? When both A and B are 0. Then you can just consider, no matter what the carry in is, just delete it. Am I making sense? This is too much into computer science. This is computer engineering course. I'm not going to anyways go into too much detail. But let me give you one more example. Generating a carry. We generate a carry when both A and B are 1. You see that? Both A and B are 1. What do I mean by generate? See, the carry in, this is carry in. Carry in was 0. I don't care. Generate a carry. Here, carry in was 1. I don't care. Generate a carry. Right. That's how they define this. Okay. It's how you see this. Okay. How can I mathematically explain this fact that only do something when A and B are both 1? I can define it in a way just by using an AND gate. Right? An AND gate will give you active output when both the inputs are 1. Right? So they looked at this, the computer scientist looked at this truth table pattern, and I haven't described the propagate. It's a little bit more complicated. Again, I'll be more than happy to go through any of these details with any one of you if you are curious, but I don't want to bore you guys and kill time unnecessarily. Okay, now just take a look at these 3 equations that they came up with, the computer scientists. Generate is AB. Propagate is A XOR B. Delete is A B. In some textbooks, they use kill instead of delete, but that term is scary, so many textbooks get rid of that and use delete. Okay, generate, propagate, delete. Can you guys, remind me these 3 things when I go to the next slide? Let's go to the next slide. Here, let's see. Generate was AB. Delete was, yes, A prime, B prime. And propagate was A XOR B. Okay. Let me just show you one thing here. This P bar P that you see here, this is nothing but this propagate signal. So apparently these circuit designers, the planners for this circuit, they implemented the propagate and generate and delete signals, right? In fact, they didn't use the delete and generate signal that much. They just used the propagate signal mostly. Am I making sense at all? Okay. I know it's confusing. That's why I warned you, didn't I? Okay. Okay, let's see. We're thankful that we have CMOS. Let me show you. In this portion, can anybody help me find this logic function? Oh, I didn't bring in two more things. So you know propagate general DNI, but what do I do with it? The last two equations are important. The last two. You can express the sum and carry function using the propagate and generate signal. Do you see that? Sum is propagate, XOR, carry in. And carry is G plus PC. Okay, so let's see. Sum is propagate, XOR, carry in. Okay, and carry out is generate plus PCI, propagate times CI. Who did that? Computer scientists. I mean, they came up with an alternative representation of this Boolean function for sum and carry. How does that help? Simplifying the circuit in some cases, if you call this simplification. Okay, now let's see. Can you guys help me find this function? Anyone? P bar C bar plus PC. I don't know if that makes sense. Yeah, we haven't, really used this circuit logic family too often, but just let me help you out. P bar C bar plus PC. This is nothing but, let me tell you, XNOR. How many of you remember XNOR operation? XNOR is AB plus A bar B bar. And what's XOR? AB bar plus A bar B. Okay, we have used that before, by the way. And you know that if you take complement of XNOR, you get XOR. They're just opposite to each other. Am I making sense? So here, what are you getting? Are you getting XOR or XNOR? No, XNOR. You're getting XNOR at this node. Okay. P bar C bar, PC. XNOR between what? P and C. C is carry in, by the way. How can I get XOR? What is that? CMOS inverter. So we are just inverting this XNOR and getting XOR. Why am I taking X? I'm taking P XOR CI. What is that? Can anybody tell me? Sum, right? That's how I'm getting the sum. And you can go through the exact same chain to see the carry and vice versa. But again, don't worry too much about it. Just wanted to show you that there is this alternative topology. Okay, I'm not going to test you in your exam on this, so don't worry. All right. That moving, setting that aside, you'll see the next topologies will just talk about the principle. Why? Because none of these are cutting edge at this point, right? We have discussed the cutting edge in full detail, CMOS inverter, and you are working on a project on the cutting edge. And the other things are there for you to know that they're there. That's it. Okay? Now, this is another approach that people proposed using delete, generate, propagate, all three. And by the way, there are added topologies beyond what we are talking about, in this course. They are way more complicated, and I certainly don't want to scare students away from computer engineering simplification. Okay. Anyways, so when you go to Intel, they are certainly not going to use the topology that you are designing for your course. I mean, they have definitely come up with better designs and more complicated design with more features, of course. But you will learn if you decide to join a particular company. They will train you on. No worries. Anyways, are you guys with me so far? If you listen to me, this will be over very soon. Okay. Let's calculate the carry. How many of you remember generate, delete, and propagate signal? Generate was no matter what the carry in was, just create or generate a carry. That's what generate does. What's delete means? No matter whether you had a carry in or not, delete the carry out. There will not be any carry out, right? Okay, let's see. This is generate signal, and this is what? A PMOS. When this PMOS is activated, this output will be what? 1. Am I making sense? So if you provide the generate signal, carry will be 1 for sure. So it's generating. Will? No. Oh, yeah. I was going to talk about the bar. Yeah, thank you. I'm glad that you noticed this. Okay. But for the time being, ignore this. Just imagine that you are providing a generate signal. Okay. You're providing a, hey, generate a carry. The problem is the PMOS. The PMOS doesn't like high input, right? It will not turn on with high input. How can you turn on the PMOS with a high input? Take bar. You are calling this to generate. G is 1 means generate, but that will not turn on the PMOS. So you have to invert. That's why. But essentially, you are just instructing the PMOS to activate itself and charge up this output. How about delete? See, there is no bar here because NMOS is fine with high input. So when you say that, hey, go ahead and delete the output, this carry will be taken to ground. Done. As simple as that. See, so the efforts that computer scientists took, it helped us simplify this circuit design. Make sense? This is actually really nice and elegant design, by the way, as you see. And what else? Propagate. Okay. If the propagate signal is high, let's see, if PI is 1, then this NMOS is on, PMOS is also on, because this is PI bar. Then you just connect this carry in to carry out. See, propagate what you have at the input. Propagate, just give it to the output, done. If you have 0, output will be 0. If you have 1, output will be 1. Doesn't matter. Make sense? If not, don't propagate. Does that make sense to all of you guys? Okay. What you do not see here is that how do you create this delete, generate, and propagate signal? Don't forget that propagate needs its own logic operation. Generate needs its own logic operation. And delete needs its own logic operation. So although this circuit looks simple, oh, you just have 4 transistors. You need more transistors to calculate this actually. Okay, so don't forget that. Am I making sense? Okay, but this is an interesting way that they thought about, they presented. And by the way, just to give you some sense, the dynamic logic design is actually always interesting and people think about it. This is the same logic gate implemented in a dynamic fashion. You see, you have generate, propagate signals. You don't need to use the delete signal. There is a reason, but these PMOS and the other PMOS, these are the signature of dynamic logic. Am I making sense? I don't want you guys to worry too much about it. I just decided to keep it here to show you that dynamic logic is often brought into the design mix, right? If you take the effort to understand this circuit, it's not going to serve you anything. But if you take the effort to understand the principle of dynamic logic design, then maybe in the future, if you ever work on circuit design, it will come in handy. Am I making sense? So this circuit is exactly the same as the one on the left, but we have implemented the dynamic logic here. One of the ways to understand that this is dynamic logic would be to see this. This phi is often used to represent clock. So when you see you have a clocked circuit, that means it's a dynamic circuit. The clock controls everything. Any problems so far? Okay. And don't hesitate. I mean, if you have problems, many of your friends are using my office hours. So why shouldn't you? Okay. Please do consider visiting me during my office hours, or even beyond, by the way. If you want, if your office, my office hours do not work, if you have classes or something else, you can always send me an email. I typically try it, and it happens quite often. I try to find time, you know, other days, other time spans to sit with students. Okay. So make sure you understand what is being covered in the course, if you actually care about this contents. And there are some contents that you should care about, even if you don't like that. like dynamic logic, like I said. Yeah, these are important for your exam. And there are some concepts that are not going to be, you know, that important for your exam. I don't want to make your life difficult, and especially because it's not really cutting edge, like this one, for example. Okay, I just told you there will not be anything related to this particular transmission gate-based error in your exam. So if you don't care, don't bother. But if you do care, if you want to learn more, I'll be more than happy to sit with you and go through this step-by-step detail as to how this circuit works. That's what I'm offering you. Okay, now moving forward. See this circuit? This is just one bit adder, right? Just single bit adder. Guys, can anybody tell me how to make a 4-bit adder? Just to remind you. Okay. Can you guys help me? A0, B0, 2 inputs. You have carry in, you have carry out, and you have sum. Sum 0 because A0, B0, right? Carry out 0. And you have the exact same thing. Just literally copy it over to the side and connect the carry out as a carry in for the next stage. And then you have sum 1, carry 1. This was, say, carry 0. Any problem? And so on. Just keep connecting them like this, like a Lego blocks, right? Do exactly the same thing for this guy. That's what's shown here. This is taken from a textbook. I just wanted to show you. I thought, oh, the students will just have a look at one particular adder cell. That doesn't give them the sense as to how the overall system works. That's how the overall system works. Let me show you. Getting back, you have header PMOS, footer PMOS, right? You see that? You have header PMOS, footer PMOS, header, footer, header, footer, header, footer, everywhere. It's exactly the same thing everywhere. Let me just mark one of these cells. Just take this cell and copy it everywhere. Does that look similar to the one that we saw before? Are you guys confused or what? Make sense? Okay. So there is nothing special about this circuit except that it shows that you can cascade, right? You have to have multi-bit addition. That's why. Okay. Moving forward, you'll see we will be just covering the high-level concept, and that's how it's done in textbooks as well, right? They mostly touch upon this high-level concept so that you know that they're there. This is another concept of implementing an adder. It's called a carry bypass adder. You see, the problem is always with the carry. Can anybody remind me why we are so concerned with carry propagation? Carry. Why? Why are we so concerned with the carry?
Because it causes delay.
Because of delay. Thank you. Remember this chain which I was drawing? This guy cannot give you the sum until what happens?
C1
it already
is
has A to B2, by the way, to start with. It already has A to B2. What it doesn't have is what? The carry. It will wait on the carry. So the carry will have to go from here to here, and then you will compute. Especially when you have, say, 64-bit adder. The 64th bit will wait on all the other stages. Hey, man, I'm still waiting, right? So that will be the slowest signal through the chain. So we care about carry. If we could somehow speed up the carry or give the next guy a hint, hey, you're going to have a carry of 1. So start your computation. That will speed up the process. So that's what computer engineers design. For example, this is one approach which often works. It's called carry bypass. Let me explain what it means. So you have, before I begin, to explain this circuit, you need to understand what FA means. FA is a full adder, okay? Full adder. Why? What do I mean by full adder? The adder that has A, B, and carry in 3 inputs is called a full adder. It's capable of the entire thing. But oftentimes we design a simplified adder with just A and B. We don't consider the carry. Consider the very first adder that you used here in this design. You actually do not need this carry in, do you? This is the very first bit that you're adding. There was nothing before it, so you don't need this, right? And what is the function for a sum operation in adder? A XOR B XOR C. Any problem? For the first adder, do you have any C? The very first adder in the chain, you don't have any C. Can I write that sum would be A XOR B? Any problem? What is A XOR B? AB bar plus A bar B. Just two terms. As simple as that. Do you guys remember what A XOR B XOR C was? Remember? I know I'm going back and forth, but it's important. A XOR B XOR C was this. See? Is it not complicated? And to implement this, you needed more transistors. Okay? So even if you could just replace one adder with a half adder, right? Rather than complicating the design, you can save a lot of transistors. Remember this, okay? So oftentimes in many designs, half adders are used instead of full adders. When you recognize that you don't need to use a carry in, you just replace the full adder with a half adder. And this thing will keep coming back in the next lecture, lecture 10, you will see. So I just wanted to give you a heads up. Okay, so here, so far we have been using full adder. We'll keep using full adder. Now, you have a carry in to this chain, this carry in. And you have all the other adders which are, doing its thing, doing their things. Carry, 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 nothing special. They're designed to behave like a ripple carry adder, simple ripple carry adder, the one that we know so far. But you have a additional signal called bypass. BP means bypass. It represents bypass. Okay. You use a logic gate to compute this. What is that? Propagate. Remember P? That's what does that mean? Propagate, right? If P0 is 1, what does that mean? Propagate the carry for the first stage. Are you guys with me so far? Okay. If next one is 1. By the way, there is a typo right here. It's taken from a textbook, but I guess the textbook had a typo. Am I making sense? This is P0, G1. This will be P1. Let me see. Oh no, I think that's fine. That's fine. That's okay. Okay. The fact is, imagine if your propagate signal is 1, right? Then this guy will propagate the carry. If the next propagate signal is 1, then this guy will also propagate the carry. Next propagate signal is 1, this guy will also propagate the carry, and so on. Make sense? When can I say that the initial carry will be finally propagated to the last stage? When propagate, first propagate, and second propagate, and third propagate, and fourth propagate, all of them are 1. Make sense? Then I should bypass the carry. Can I say that? Don't worry about it. Just bypass the carry to the 4th stage. And you can do it to the 8th stage, 10th stage, up to you. But this is just an example. Okay. So we actually calculate this signal called bypass. If this bypass is 1, that means you eventually be propagating this carry throughout, this design. Then all you do is you just bypass this initial carry to the 4th stage. Make sense? How many of you remember multiplexer? What does that do? So switch between 2 inputs, exactly. So, by the way, what if this bypass is not 1? Then what do you do? Anyone? You just literally follow the regular chain. You don't have any other choice. This is just an extra feature. See, maybe Intel introduced, I don't know whether it was Intel, okay? I'm just making it up. Maybe Intel introduced this feature sometimes in their design. And that's how their errors become faster than some other, companies say. And the other companies have their own tricks. Make sense? So you either bypass if possible, if not, just go through the chain. And then the multiplexer decides whether to wait for this chain or to take the bypass input automatically, depending on the bypass as a selector. Okay. That's the idea. And this is another implementation. Carry bypass in Manchester carry chain adder. You haven't seen Manchester carry chain adder. This is what a Manchester carry chain. Anyways, we don't talk about the full circuit. This is another approach of using the same thing that I just described. Okay, let me show you. This is how the bypass signal comes into play. Propagate, 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 propagate. You see, this is carry. Only when all of these propagates are 1. Let's see. This is 1. This is 1. This is 1. This is 1. What will be this bypass? This will be 1. Any problem so far? Only then this will be provided to the output. Any problem so far? Okay. Now, there is one other parallel branch as you see here. If bypass is 0, okay, I think there, there is a, again, I mean, these textbooks often have an issue. So this should be a PMOS. Okay, you see the point? When bypass is 1, then this NMOS is on and it will just bypass this all the way to the input. But when bypass is 0, when bypass is, this, remember, this is a PMOS. When bypass is 0, then this guy is off, but this PMOS is on. Yes. Well, it will, but there is no purpose of the transistor in that case, right? You could either use, let me show you, you could either use bypass bar with an NMOS, or you could use bypass with a PMOS. Am I making sense? It will work, it will work, but there is no reason to have this parallel branch back there. That's what I'm saying. Yes.
For the generating signals, what's keeping the signal?
That's a great point. That's a great point. What's keeping this, as you see, the generate signals are connected to the drains or source or whatever you say, right? The problem is, in this circuit topology, there is always this problem. These signals can interfere with each other. That's true. There is a possibility. But there is a logical advantage to this. Let me show you. This is a great question. I mean, it takes some explanation if you give me a few minutes. Okay. Propagate is A XOR B. Generate is AB. Let me actually draw the truth table right here. A, B, this is propagate, this is generate. 0, 0, 0, 1, 1, 0, 1, 1. Let's first do propagate. What is propagate? A XOR B. This is 0, 0, 1, 1. Am I right? What's generate? AB. You have 0, 0, 0, 1. Do you see something interesting? There is no scenario where both propagate and generate signal will be 1. They will never be activated together. Okay, that's what they're relying on. That's a great question. And actually they thought about it. And that's why they're connecting it this way. Make sense? Okay. All right. But folks, don't worry too much. Even, you see, there is just one circuit right here. Why? Because we don't care that much about it. Okay. So if you're curious, like this great question, if you have questions like this, I mean, I feel really great to go through the details. Okay. So please don't hesitate. Now, the point is, this is another approach, just an approach that kind of relates to this carry bypass adder principle that we discussed right before. There is another approach. Let's talk about it. Oh, before we go there, let's see a system level perspective again. Here you are actually adding 16 bits. How do I know? This is bits 0 to 3, 4 to 7, like 4 bits at a time. Right? This is again taken from a textbook, of course. Now, and by the way, the textbook descriptions for these things, I mean, I don't know about you, but it was really confusing for me when I was a student. That's why I decided to just cherry pick different figures from different circuits to create a flow. I didn't want my students to go through this because, to be honest, that's how you lose most of your students. And they decide, oh, circuit design is not for me. It's not that bad. I mean, it's actually logical. The flow is logical as long as you don't get lost into the description of the text. Anyways, let's see. This just shows you the overview. You have a carry in coming. You have the carry propagation chain. What does that mean? This simple carry propagation block actually represents this block. Am I making sense? Through which the carry actually will have to propagate. The carry cannot be bypassed. Okay, so you have a carry propagation block which actually has multiple blocks inside. Make sense? Okay. And then what is that? Bypass. And this is the multiplexer that you had, which chooses between the bypassed line and the propagation line. So, and then next, exactly the same thing. Copy, keep repeating. For this particular design, the circuit designers have chosen to test 4 bits at a time. They just check with 4 bits. Should I propagate the carry? Okay. And after 4 bits, they again repeat it. Couldn't I do something like this? Testing, instead of testing 4 bits, couldn't I check 6 bits like P4 and P5 all together and then propagate 6? That way it will be even more accelerated, right? Do you guys see any problem with it? Do you guys see any problem with it? Anyone? Imagine you are an engineer sitting in a meeting room. Your colleague is presenting something. If you can come up with a problem with your colleague's idea, I mean, you get the promotion. If not, he or she gets the promotion. And now it's up to you. It's not always about promotion, by the way. People get laid off. If they're too unresponsive for a longer period of time, that means they're not useful to the team. Okay, they're not bringing in anything. You either point out a problem or you point out a solution to the problem. If you don't do anything, okay, just keep proposing. I'll just be there, get coffee, something. Right now, being in that scenario, somebody asked your colleague who presented this idea that, hey, okay, so why have you chosen 4? Why haven't you used 5 or 6 or 7? Why not more? Conceptually, no problem. There is one practicality problem. Can anybody tell me what that is? Sorry. That's true. Okay, 8, 16. I mean, these are all standard, right? 4, that's not the real reason. I mean, the reason is, that's a good comment, by the way. Yeah, sorry. Yes, that's one reason. Thank you. Well, imagine when you have P0, P1, P2, P3, look at the chain. P0, P1, P2, P3. You need to implement that as a logic gate, don't you? You already have 4 transistors stacked up. We don't like it, do we? Remember, we don't like stacked transistors. Now, if you bring in even more, that will be problematic. Make sense? So that is one of the reasons why, you know, we typically just don't go beyond. Yes. Yeah, if you stack too much, remember, let me just remind you that problem we discussed. 1, 2, 3, 4, and most. Remember that capacitor? We discussed this before in the course. This is your output, okay? Yes, yes. Thank you so much. Yes, that's exactly what I was hoping for, and I was going to tell you. And you know, you beat me to it. This is a reason which is related to circuit design. There is another reason which is related to computer science and probability theory, which means, what are the odds that all 4 of them will be 1? Imagine. Pretty small, like 1 in 16 maybe, if you think about it, right? So the probability of just imagine in 1 in 16 scenarios, there could be 16 possible combinations with it, right? You see that 0, 0, 0, 0, 0, 0, 0, 1, and so on. 1, 1, 1, 1. Only when you have this one, you activate the bypass. Other than that, you never use it. So what's the, I mean, it's not, good to assume that you keep having this combination. It's already improbable, almost. 1 in 16, what are the odds? I guess you have better odds at winning a lottery sometimes. Anyways, that's exaggeration. But the moment you bring in one extra bit, P4, right? Then the odds become 1 in 32. One more extra bit, 1 in 64. So the probability of ever activating this path becomes lower. Does that match with your, thank you. That was a great answer. Yes. So because of these reasons, we don't typically, use more than 4 bits or something like that. And as you see, this is a overview of the delay that we get out of a ripple carry adder, the adder that you will be implementing in your course, and the carry bypass adder, which we are discussing right now. This is the ripple carry adder. The delay increases with the number of bits that you're adding. Why? Carry will have to propagate gradually. If you have 64 bits, 64th will be waiting. So that's why the delay increases as you have more and more bits to add. However, you see your carry bypass is even worse. It has more delay. Whenever you have less than 4 bits. You might be wondering, 1 in 16 is still a bad odd, right? Why are we even not going, using 3 bits or 2 bits? Make sense? Why don't we go the other way? Like, why don't we just get rid of this 2 and make it P0, P1? You could do that, but remember, you are using additional circuitry. You are using a multiplexer. You are using a route or something, right? Interconnects. You are using additional circuitry to achieve this. And that will add to the delay. And that's why the design will become even worse compared to the regular design that you have. Make sense? Yes. Depends on how you implement that. Typically, a mux is this, right? You can easily imagine you need 2 transistors for this, 2 transistors for this, 4 NMOSes plus 4 PMOSes. So 8 at least. And then you have an inverter, maybe, if you want to. So maybe 10, up to 10 in transistors. But you can have different types of mux. You can have transmission gates and whatnot. But lot, you see, that's a lot. Maybe 4 to 10, depending on how you implement that. So even if you have to use 1 extra transistor, that brings in additional delay. That's why the design will not be good for lower, bit operation. But as you go for higher number of bits, this wins over the ripple carrier because of the acceleration that you can get. Maybe this one didn't propagate, but maybe this one propagated. That saved some delay. Makes sense? It's kind of like a relay race. You are taking a shortcut right here. Just to end with an example, this guy tried, failed. This guy succeeded. This guy tried, failed. This guy succeeded. Still, really good performance boost. Make sense? Okay. Carry select adder, another principle. And as you see, there is no circuit here, right? This is just going to show you the principle. Circuit implementation will be complicated. If you're interested, we can dig deeper. If not, don't worry about it too much. The approach is, the proposal is that you store both, the carry could be one of 2, either 0 or 1, right? You already know the answer, 1 of 2. You just have to pick between these 2. Make sense? Why are you propagating the carry? The question is, why are you sending this carry all the way through the chain to the other end? Why don't you just select the carry, which is already stored? Make sense? By some sort of indication. And here is how they propose doing that. You have a 0 carry stored, 1 carry stored. You have a multiplexer that chooses between the carry. And again, these are taken from different textbooks. That's why they look different, they don't even use this type of multiplexer symbol. They used a different type of symbol. That's okay. Make sense at all? So you have 0 and 1 stored, and you have a multiplexer, you have a sum generator. You somehow select whether to use 0 or 1 as the carry for that particular stage. How do you select that? By calculating these signals, which is there, propagate or generate. Let me actually give you a high level overview right here. That way it will be easy. Make sense? All I've done is taken this and copied and pasted it in multiple sections. That's it. Bits 0 to 3, 4 bits, 4 bits, 4 bits, 4 bits. Okay, now let's see. As you see, you have 0, 0, 0, 0 stored everywhere. You have 1, 1, 1, 1 stored everywhere. Everyone has a 0 and 1 stored somehow. You just need to choose whether to take in 0 or to take in 1. You just have to choose between them. Makes sense? And it's not shown here, obviously, the circuitry. You can use the propagate and generate signal and delete signal to figure out whether at this given point, you will end up getting 0 as carry or 1 as carry. Making sense? So they redesigned the overall principle of adder design. Instead of going through the chain propagation, they started calculating in place. Makes sense? We will see the detail of one last circuit before we end, by the way. So we are kind of skipping this. We will see an interesting circuit, which I really like. I'm saving it for the last. Okay. But we are skipping the circuit design for this, just principle. Okay. So you use some circuit, in between circuitry to calculate, propagate, generate, and delete. And you can figure out whether to just use 0 or just use 1 for this particular block. Make sense? And then you just generate the carry. So there is no propagation. You see the point? Okay, so that's the carry select adder, which selects the carry, whether to select 0 or to select 1. And it may not be possible, by the way. Remember, similar to the problem that you had here, you may be able to bypass, but there is a possibility that you wouldn't be able to bypass. Remember, depending on how the logic turns out, you can either bypass or you have to go through the chain. Same thing remains here as well. Can you select between 1 and 0 somehow? Or we cannot tell because we are not sure. Then propagate. See, the option to propagate is still there. Propagate. You still have the propagation chain. But if for some reason you're able to predict whether this carry will be 0 or 1, you just select it. You don't propagate it at all. That means, what is the difference between the bypass and select? Can anybody tell me? Bypass still propagates, but not through the chain. Bypass propagates through a different channel, right? It still provides through an interconnect. But the select doesn't even provide through an interconnect. It just chooses from the stored value, either to use 0 or 1. Am I making sense at all? It's difficult to just explain the principle with the circuit, I know. But I think that's good enough for this particular topology. This is the really last slide for this lecture. And this is one of the most important topologies that I would like to discuss in this course. Carry look-ahead adder. The name will probably not make a lot of sense, and these are taken from a textbook. And like I said, they're really good at making things look complicated. So don't worry about it. Let's work on it together. You guys ready for it? Okay. This is the circuit, by the way, for carry generation. Looks really nice, like a spider web, right? And we'll make sense of this spider web soon. Let me start with this. Remember this carry out function that we just discussed a few minutes ago? Let me just make it smaller. G plus PC, because I'll need some space. Let's work on it together. Okay. Carry out. This is the carry in. So the carry out of a given stage, let's consider that this is stage K, is the generate of that stage and propagate of that stage and carry in of that stage. Or can I say the carry out of the previous stage? Let's see, carry out of a given stage, kth stage or ith stage, whatever. Which one do you like, K or I? Tell me. K is good. Okay. K, given stage K. Generate of that given stage, propagate of that given stage, and carry out of the previous stage. The carry out of the previous stage will be carry in of that stage, right? Any problem so far? Let's use this to calculate. So you have A0, A1, A2, A3, 4-bit. B0, B1, B2, B3. Sum 0, sum 1, sum 2, and this is the last slide. So let's just get it done with, okay? And carry 0, carry 1, carry 2, carry 3. Let's see, it's gonna be fun. Let's first calculate the first carry out will be generate of that first stage. 0 means first bit, by the way, you know, 0, 1, 2, 3. 3 is the fourth bit. Propagate of that stage and carry of the actual input, the real carry in, the primary carry in, which is often 0, by the way, as you know, right? Okay. What is the carry 1? It's gonna be generate 1 plus propagate 1 plus carry 0. Does that make sense? Please try to, you know, double check that with this ideology. Are you all good with it? Okay. Can I replace this carry out with this equation? Anyone? Can you help me do this? G1 plus P1 G0 plus P0 C in. Let's just calculate this. G1 plus P1 G0 plus P1 P0 C in. This is C1. Okay, any problem? Okay, let me use a different color now. Okay, what's C2? C2 would be G2 plus P2 C1. Can I replace this C1 right here? Can I do that? Okay, so if I do that, I'll get G2 plus, let me just actually multiply this, okay, to save time. P2 G1 plus P2 P1 G0 plus P2 P1 P0 C in. That's what you get as C2. I'll just keep it right here. And I'm running out of space. So I will just erase the ones that are on the top because I've already calculated C2. Let's take the final step, C3. C3 will be G3 plus P3 C2. And you already know C2, don't you? Can I replace C2 here? So I'll get G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 C in. That's C3. Any problem so far? That's it. That's it. Okay. So that's the mathematics that computer scientists do. Now, here is what computer engineers do to implement that. Ready for it? Last 30 seconds. Can you help me identify this P3, P2, P1, P0, C in? If I try to implement that in a CMOS circuit, how many NMOSes will you have in series? 5. Do you guys agree with it? Remember the names: P3, P2, P1, P0, and what? C in or CI, whatever. Let's go. See, P3. P3, right? You see that? That's the input. P2, P1, P0. What's that? CI. Got it? Okay. So that's done. How about this guy? P3, P2, P1, G0. P3, remember these terms, P3, P2, P1, G0, right? Let's see. Let's start with G0. This is G0. You see that? You see that this is G0? And this is an NMOS, by the way. G0. And let me use a different color maybe. This is G0. What is that? P1, P2, P3. So P1, P2, P3, G0. What is that? The second term. You see the point? So essentially you keep doing that. You just literally implement this through the chain. You want me to do one more? Say P3, P2, G1. P3, P2, G1. Let's use blue color here. G1, this is G1. That's G1. So G1, what is that? P2, and this is P3. So you have P3, P2, G1. Does that make sense? Don't worry, you don't have to memorize this circuit. You don't even, I'll not even test you in the exam on this. But if you understand, it's a really nice, elegant circuit. Okay. So that concludes our adult lecture. Thank you so much.